All right, Mr. McKinney here, just talking about continuity. So if you can draw a function without picking up your pencil, then that function is continuous. Video over. Oh, wait. Okay, so let's talk about it in a calculus sense. So let's think about whether or not a function is continuous. So we want to determine if the function f of x equals 1 divided by x is continuous. And we know what the graph looks like because we studied that algebraic analysis worksheet or that parent functions worksheet from the first day of school. So if I graph this function, we've got a horizontal asymptote at y equals 0, a vertical asymptote at x equals 0, and then the rational function approaches those asymptotes in the first and third quadrant. So is it continuous? Well, we can see that it is definitely not continuous at this asymptote. The vertical asymptote is where it stops being continuous. Now let's think about it in terms of specific intervals. So let's think about what that picture looked like. It doesn't actually touch anywhere on the y-axis. It also doesn't touch anywhere on the x-axis. All right, so I want to determine if this function is continuous on the interval 2 to 7. So if I go from 2 out to 7, this entire time, yes, it is continuous. All right, what about on the interval -1 to 1? And keep in mind, in calculus, when you see something like this, you're almost always talking about an interval. Yes, it looks like a point, but this is interval notation. All right, so -1 to +1, if I think about -1 and +1. As I'm drawing it from -1 to +1, I would have to pick my pencil up. And again, that's not the calculus definition. For now, though, I can see that it is not continuous on that interval. All right, what about 0 to infinity? So starting at 0, going out to +infinity, it's continuous everywhere. And the difference between these two is whether or not I include 0. So as long as I don't include 0, then yes, it is continuous. If I do include 0, then we would say no, it is not continuous because at 0, the function is not defined. And we'll get into the actual definition here in a second. At the point x equals 2, it is continuous at that point. It's not really an interval, but it is continuous at that point. And at x equals 7, it is continuous at that point as well. And on the closed interval from 2 to 7, it is continuous on that interval. All right, now if we talk about the actual calculus definition of continuity, and this is the part that you want to make sure you get in your notes. If you don't write down very much, make sure this part gets into your notes. In order for a function to be continuous at a point, x equals c, then 3 things need to be true. Number 1, the limit needs to exist. Number 2, the function needs to exist. And then number 3, the limit and the value of the function are equal to each other. So the limit is the value of the function at c. And again, if we're talking about at a point, all of this stuff is happening at the value x equals c. So the limit as x approaches c of the function is equal to L, some finite number. This has to be a real number. And then the function exists at x equals c. So the value of the function is equal to m. That also needs to be a real number. And the third piece is that these two need to be equal to each other. So in order for a function to be continuous, the limit needs to exist, the function needs to exist, and they need to be equal to each other. They both need to be finite real numbers. Okay, so let's look at a graph and think about it. So I want you guys to think about the different x values, a, b, c, d, e, f, and g, and think to yourself at each of those points, is f of x continuous? And if you think it's not continuous, tell me specifically which piece is not true. So does the limit not exist? Does the function not exist, or do they both exist but they're not equal to each other? So I want you guys to hit pause right now and write down what you think the answers are. All right, so let's see how you guys did. So at A, this arrow implies that it's going to keep going. There's nothing happening at A that's interesting. There's just a point, so that is continuous. All right, at B, it is not continuous. The limit exists, the function exists, but they're not equal to each other. At C, it's not continuous because the function does not exist. Also, the limit does not exist. The limit as x approaches c from the left of my function would be positive infinity. The limit as x approaches c from the right of my function would be negative infinity. Since these aren't equal, the limit doesn't exist. Even if they were both going the same direction, it still couldn't be continuous because the limit and the value of the function both need to be finite numbers, and infinity is not a finite number. All right, at D, the function exists, the limit does not. We have a left side limit and we have a right side limit, but the limit at D does not exist. So that limit does not exist in this particular case. At E, the limit exists, the left side limit and the right side limit both exist and they're at the same y value, but the function does not exist. So this is not continuous. Over here at F, some of you guys get thrown off when you see the point. That point doesn't mean anything. It's just showing you that it's part of the function. So it is continuous over here. And then at G, it's kind of a trick question. You can say that it has endpoint continuity, but you wouldn't really say that it's continuous because the left side limit and the right side limit aren't the same, but it does have endpoint continuity. Don't get too caught up on endpoints. All right. So again, you can check your work here. I've got it all written out. So hit pause, read through it, make sure it looks right. Also, I want to back up a little bit. On this step, the way you can visualize what the limit looks like would be coming from the left and coming from the right, you're at the same point. What the function looks like would be the point being defined somewhere. And if this dot fills in that hole, then the function is continuous. All right, so I just touched on this a second ago. If the function, let's look at it this way. If the limit on the left side, so the limit approaching A from the right is equal to the function, so the value of the limit coming this way is equal to the value of the function at the endpoint, we say that it has a left endpoint continuity. Same idea over here on the right. So this is just a specific way of talking about a function being continuous at the endpoints. Don't get too caught up on this, but technically at the endpoints it's not continuous, but it does have endpoint continuity. All right. At a specific point, if it is not continuous, then we would say that there is a point of discontinuity. And there's different types of discontinuities that we're going to talk about. So there are non-removable discontinuities, and those come in two varieties, either an infinite discontinuity, which would look something like this if you had an asymptote, and then either they both approach the same side, or you have an asymptote and one approaches positive infinity and the other approaches negative infinity. This would be an infinite discontinuity. A jump discontinuity is where there is a finite difference between the left side limit and the right side limit. So for example, if I had my function coming along and it was defined here, and then it jumped to an open hole and it kept going that way. This would be a jump because there's a finite distance. So the gap here is finite. That makes it a jump discontinuity. If the gap in between them is infinite, or if there's an asymptote, then it is an infinite discontinuity. And again, both of these are non-removable discontinuities. All right. There is also a removable discontinuity, which when you think of it, it looks like a hole. That's not the type of discontinuity. It's a removable discontinuity. So if the question asks, what is a discontinuity? Don't say it's a hole. Say it's a removable discontinuity, but that's going to look like a hole. And a removable discontinuity is where the limit exists and the function exists, but they're not equal to each other. So here, the function existed, and some people see that hole and they think that this is a removable discontinuity. But the limit does not exist because the left side limit and the right side limit are not equal to each other. In a removable discontinuity, then the limit does exist. So the limit exists and the function exists, but they are not equal to each other. And again, these top two are both non-removable discontinuities. This is a removable discontinuity. And then you have endpoints, and we don't really call them discontinuities, but it goes back to that slide and you can look at it again. If at the end of a function, so let's say it goes forever that way, but over here on the right side, if the limit coming in from the left, so let's call this c. So the limit as x approaches c from the left of this function is equal to the value of that function, then we would say that it has endpoint continuity, in this case, right endpoint continuity. And that says continuity. I know you can't read it, so use your imagination. All right, so that's going to wrap it up for this first video on continuity and, as a side product, discontinuity. Hope it helped.